Let's talk about hypothesis testing. Hypothesis testing is closely related to what we did before with confidence intervals. In this instance, we need to have a null hypothesis, a basic hypothesis that we're going to use in our calculations, and an alternative hypothesis that is the one that we're going to accept if we have to reject the basic hypothesis. The basic hypothesis is called H0 or H null, the null hypothesis. And let's suppose you're a manufacturer and you have a contract to build a certain object, and we're simply going to say the basic assumption is that its mean length is 7.45 millimeters. And the alternative, of course, will be HA, the alternative hypothesis, which is that you're not manufacturing it according to 7.45 millimeters in length. Let's suppose further that your requirement is that you do this with 1% significance. Okay, you want to be 99% certain that you are meeting your requirement. Of course, we know what that means. If you look at the bell curve, the nice standard bell curve, and all you care about is a two-tailed test, that is, you can't be too low or too high, that would be 0.05 on one end and 0.05 on the other end. We're just taking alpha and cutting it in half. And the usual business, 0 for your mean in the middle. And you know what Z critical is. The critical value is going to be 2.576. 76 minus 2.576. So as long as you're not in this little rejection region at the top and this little rejection region at the bottom, everything should be fine. What do you have for data? Well, let's assume that what you're doing here involves taking a sample of your manufactured item, these items of length of about 7.45, and let's say that you take 36 of them. Okay? And let's say you find out that, they're just a little bit on the long side, 7.45 in average. Does that violate the 1% level of significance that you're looking at? Well, we need more data, so let's assume in this instance, for some reason, you happen to know that the standard deviation of x is 0.027. Let's go ahead and compute the z-score for x bar. We know that z is x bar minus the assumed mean over sigma divided by the square root of n, because this is a sample mean. So we're looking at 7.46 minus 7.45 divided by 0.027, and that in turn is divided by the square root of 36, or just 6. And when you work it all out, you get 2.22 and a bunch more 2's. Well, look what we discovered. We're up here at 2.22. We are not in the rejection region, and so we're able to accept the null hypothesis. We're not rejecting it. We are in compliance with our requirement to at least 1%. By the way, there's a couple of other ways to look at this. Remember confidence intervals? If you look at mu plus or minus the error range, let's see, that would be 7.45 plus or minus, let's see, we have to take the critical value, multiply it by the sample mean standard deviation, 7.45 plus or minus 2.576, and we've got 0 to 7 over 6, 7.45, plus or minus 0.012 when I feed that into my calculator. If I subtract 0.012, I get 7.438. If I add it, I get 7.462. And what I can tell is my statistic, 7.46, I see that I made a mistake here. This is 7.46 is what I intended. 7.46 is in between these two numbers and again is acceptable. One last way to take a look at this, okay? If I come back up here and look at 2.22, I can check this on my calculator. And for the upper range of 2.22 on this distribution, I find myself looking at 0.9867, okay? So, 0.9867. Well, we happen to know that the top range is 0.05. We're looking at 995. This is to the left, and that's another basis for knowing that we have an acceptable result. That's one example of hypothesis testing. Suppose we had a different version. Suppose we were looking at a hypothesis, a null hypothesis, that says mu is greater than or equal to 10. That would be one-sided. And the alternative hypothesis would be that mu is less than 10. In other words, our rejection region would be on the low side because this is the only part that causes us to reject our null hypothesis. And we're going to assume that 10 is our average. Okay? And let's talk about the level of significance we're going to have here. Let's say it's 5%. So this is 0.05. If we were looking at the critical value for this, it would be minus 1.645. Okay? So what's going to happen in this instance? Well, let's look at the data that we collect. If this were something like we were testing battery lives and we wanted to see if our newly manufactured AAA battery could last for at least 10 hours or above, then our statistic, as long as it's 10 or above, we're perfectly happy with that. If it's below, is it far enough below to be in the rejection region? So we're assuming, for the time being, that mu is 10, based on our equality from the null hypothesis. Let's suppose that we took a sample and found out that we had a lifetime for our batteries of 9.6. Okay, let's say those are, hours. And if this had been higher, we already knew that that would be acceptable. So this is low, and we want to know if it's too low. Let's suppose we don't know the standard deviation, so we have the sample standard deviation of 8.55, just from our data. And we got it from a large enough sample, so we don't have to worry about using the t-distribution. If this had been 30 or below, we could use the t-distribution. But as long as we have a large enough sample, we can go ahead and use the z. Again, let's take a look at what our z-statistic is going to be, our z-score. We're going to have x, we're going to subtract the mean, we're going to divide by s, and the square root of the sample size. So in this case, we're looking at 9.6 minus 10 divided by 8.55, and we have the square root of 50. We work this out, and we get minus 0.33. Okay, well, minus 0.33. In that case, let's take a look at where we are. Our critical value was minus 1.645. We only went down as far as 0.33. So again, we get to accept our null hypothesis that mu is 10 or above. There are a couple of other things that you can do to take a look at this. For example, if you take a look at the error range, E, which would simply be our critical value times our standard deviation sample over the square root of n, we'd be looking at 1.645, 8.55, square root of 50, work that out. We have about 1.98. Okay, well, 10, which is our average, our mean, minus 1.98, because we care about the low side, is 8.02. Well, what did we get? We started off with 9.6. So again, that is in the acceptable region, and we were able to accept our null hypothesis. So that's a second example of hypothesis testing.